looks like we can start. Welcome back, everyone. We got through our first exam, so congratulations. That's always kind of tough and stressful to get through, especially the very first one where you're getting used to what exams even look like in this class. As far as exam one goes, I should have this completely graded on Friday, probably around, if I had to guess, around 2 p.m. or so. I'm going to upload the results to Moodle directly and update your current course grade, taking into account your exam score, quiz score, and your grade in the MyStats Lab homework system, I guess is what we call it. As far as that goes, what I'm going to do after I upload that information, I'll go up here and just make a forum announcement. That way, if you like, you don't have to click on this a whole bunch of times waiting for your grade. You can just wait till the email comes through to your ISU email, and then you'll know grades are available. After that, they'll be returned to you, the hard copies, on Monday's class. So that takes care of our exam one. Then looking ahead, we don't have a whole lot going on in the weeks down below. If I scroll for just a touch, we do have a midterm week, but we're not doing any special project. There's no particular exam or anything on midterm week. We'll just be reporting your grade as it stands at the end of that week there. Afterwards, after midterm week, it's just how it fell, we'll have our second exam. That exam pretty much is just going to pick up right where this one left off. Left off in section 2.5. And so we're going to pick off on chapter 3 right here. These are kind of like single sections. If you see just a whole entire chapter being represented this way. So there's not going to be a whole lot of questions from chapter 3 nor chapter 4. You could expect more questions from chapter 5 just because it's being split up into different parts like this way. At least one question per section is what you could expect. But like we did with the originals, week 1 all the way through week 5, as soon as we get closer and closer to this week right here, we'll post the information on the definite coverage, study guides, and that kind of stuff. So basically everything just repeats almost like a ritual here in the Moodle website. So that's where we're at, where we're going so far. At the moment, we're about to finish off section 5.1. We're talking about z-scores. These are the relevant formulas just as a doodle, also on the notes, so don't feel like you have to scramble to copy them down. Then we'll be looking at shifting and scaling. All this is finally getting towards the normal distribution where we'll once again be using the calculator for lots of computations to see how all that goes. The major thing we've been doing in the calculator has been just hitting stat key, importing data, going over to calculate the data. But once we get further in chapter 5, we're also going to be using this feature. If you hit the second button, and then the button that says vars, that pulls up distributions, we'll be looking at the normal CDF and inverse normal to look at how to answer certain questions in chapter 5. So that'll be our major thing on coming up with the calculator so far. I think that's my whole spiel for announcements today, folks. Any questions or comments at all so far? Okay, well, let's see where we left off. In section 5.1, we left off right on example 2. And so continuing from here, this is kind of like just an extra practice, very similar to the example 1 we did, but more of a contained problem, not as much information. Here's a reminder about z-scores. What does a z-score do? Well, in words, it takes a data value. When it says data value, it's referring to this y right here without a bar, so just one observation in the data. For example, these are the data values in the problem given. Then we subtract off the mean, divide by the standard deviation. That has a lot of interesting effects we're going to find out in section 5.2. So we'll be talking a lot more about mean and standard deviation going forward in chapter 5. What we didn't hit on a whole lot about the z-score is there's a lot of ways to view what this does. If you're subtracting from if you're subtracting y bar away from y, divide by s, what you're really getting is this. You're finding out how many standard deviations you're away from the mean. And, well, this doesn't seem like a much, but sometimes questions are about that statement right there, which can be surprising. So it always pays attention to think of the z-score in those terms. It's always the number of standard deviations. Any questions so far, folks, with the formula? Okay, now let's apply it then. This example is, kind of boring, looks like just an ordinary math problem, but it gets us right into the formula, working with it directly. We have a random sample of 6 light bulbs. So in this problem, we have a sample size n equals 6. They were selected from a production line and their lifetimes were measured in hours. So here are all the light bulbs. You can imagine maybe this is something like cheap LED light bulbs, companies trying to maximize profit somehow, so they have a new production line. But to test out their claims on their packages, they need to have a little bit more control on what's going on with these things. So they took a random sample of size 6, and probably next thing they want to know is some summary statistics. Part A says, use a calculator or computer. This is kind of weird. This is more if you're working at home, but I would say using your calculator is the major way we're going to do this, to find the sample mean and sample standard deviation of these data. Well, notice how this question is being asked. It's not asking you to find y bar, although it said it in words. It's not asking you to find s, although it said it in words, standard deviation. So part of the battle here is just knowing what these things are referring to each time you see them. That's part of what's going on here in the bracket with the star on it. If this ever comes up, we have to think, oh, that's about z-scores. Much like when this comes up, we have to think, oh, that's just the sample mean y bar in the calculator, or x bar is how it comes in. Well, first thing we have to do is the ordinary mantra of hit the stat key, hit enter. You have data in there, probably from the last exam. Up arrow, hit clear and enter. So now it's wiped out. And we'll just type these in one by one. So 968 to start. 893 hours for the second light bulb. 769 hours, 845. 922, and then finally 915. So with the data imported, next hit your stat button, right arrow to calculate, and if you feel like this is kind of boring, then that's awesome. That means you've probably done this dozens and dozens of times. You've got it down to your muscle memory. And that's kind of the goal, to not be so foggy on it while you're doing an exam. You want to have it down pat by the time you're going into an exam. But you're always welcome to have a page of notes that describe those instructions to help out. So hit enter here, whole bunch of enters, and we just needed 2 things. The sample mean is indicated by this value right up here. We're rounding to 2 decimal places they're indicating, so almost call that an X. That's a thing I'm trying to correct. My last book, we used X bar, now we're using Y bar. That's really hard to change a habit on. So it's 885.33 hours. Something went wrong with this 8 here. Let me see if I can fix it. Next, the sample standard deviation S. This is always an easy thing to make a small mistake on. Is it 69.68 or is it 63.61? Good call. The trick here is if it's a sample standard deviation, which is what we're almost always calculating in a class like this, it's always the larger number, but it's also indicated by S. So S or X, or it'd be SY if you wanted the extra symbol, comes out as 69.68. So we have our summary statistics. That means we can use a formula like this above for a z-score. So with those down, that's kind of the review portion of what we did on exam 1. Here's the next follow-up question. They say, suppose another randomly selected light bulb, so something not on this list now, is tested and runs for 693 hours. Maybe it's an independent lab verifying claims. We want to now know how many standard deviations away from the mean is this observation? And that's a really rough way to ask a question, in all honesty. The nicer way to ask that question is just to simply say, what is the z-score for that observation? But watch out for when it's verbalized like this, because that's not too uncommon, just simply to ask that for that information. So what they're saying is, coming back with that same color, let's say i.e., what is the z-score? So that's the toughest part about part B. Does that make sense on how that question was asked there, why it's a z-score? Okay, coming back up here, the z-score tells you how many standard deviations the data is away from the mean, so it's the right thing to calculate. And we just have to use this formula above. So it's a pretty fast computation. It's just a confusing way to ask the question. So z equals, we need a data value, but that's this value that was just supplied right here, 693 hours. So 693 to start. Exactly. We're putting in for y bar that value just stated. So 885.33. Then loads of the stuff you might have noticed is just substituting a symbol for a number. It's supposed to be s down below. So another mathematical substitution is grab that number, 69.68, but go in place of s. Then we're pretty much there. We just need to run this through the calculator. So let me hit, you could just hit clear if you need to get off this screen. I'll go with the parenthesis in the numerator, 693 minus 885.33, then division by 69.68. So here's our result. To one decimal place, we have negative 2.8 standard deviations. Yeah, go ahead.
Is the data value in the problem always going to be provided?
Not always. Sometimes if they tell you the z-score is negative 2.8, the question is, what is that? But one or the other would have to be given.
So if they're asking for the z-score, though, then they're always going to provide what the data value is.
That's correct, yeah. Other questions at the moment?
I got it.
Oh, could have been me. Let me see how I typed that in.
2.7601.
Oh, weird. I bet I messed up the denominator. So it's supposed to be 69.68. So let me go up here. 69.8. Yeah, let me fix that. 68. Now we're at negative 2.76 and some change.
Okay.
Thanks for spotting that. It's always weird when the numbers are just slightly off. No explanation visible up there. So we got negative 2.8. And that's a full answer. You don't have to say anything further on there. But a good habit for this kind of problem, to get away with what made Part B tricky, is if you calculate a z-score and every time you put in the unit, it will remind you what you're calculating, and Part B is no longer so tricky. So I would put negative 2.8 and grab a pen first, negative 2.8, standard deviations. You could say standard deviations and just call it good. If you wanted to, you could be more descriptive. It's negative, so we can say it's negative 2.8 standard deviations away from the mean. Well, I wouldn't want to say below the mean, because if I say a negative number below the mean, that's a double negative. So I think it's probably better to just leave it like that, so it's not suddenly more confusing than it has to be. But we did it, folks. That's our first z-score computation. Any questions at the moment with Part B? Okay, so Part B and Part C, it's more about just getting used to what the formula is, what it does for us. And here's where it gets a little bit trickier, I'd say. Kind of related on the earlier question. Part C does not give a data value. Instead, they tell us the z-score for some other randomly selected light bulb came out at 2.18 standard deviations away from the mean. Or excuse me, the z-score for another randomly selected light bulb is 2.18. Here's the question. How many standard deviations away from the mean is this light bulb?
So we need to find the data value that comes out with positive 2.18 as the z.
That's more along with the lines of this question here, where it goes, what was the lifetime of that light bulb? That's where we're going to actually solve it and find the value. I forgot I actually put this question right here. It kind of tripped me up. Anyone see what the answer should be for that one?
That's 2.18.
It is 2.18. Yeah.
That's how many standard deviations is away from it.
Yeah, it's almost a silly question, right? I feel like that one is just not a friendly trick question anymore. It made sense to ask it right here, but doing it again when you already have the value, that's just extra confusing. But let's explain it anyway. I mean, it's on the page of notes. I think it'd be a bad exam question personally. When they said Z is 2.18, the thought is, let me grab a larger screenshot. Okay, sorry, let me restart my thought. When they said the Z-score for another light bulb is 2.18, what they really told us is right out of the gate, the number of standard deviations it is away from the mean. So this question here, admittedly, it's silly. I don't think I would ask that a bunch of times on quizzes or exams. But if they ask how many standard deviations is it away from the mean, it's just the 2.18. So let's answer this by saying this observation is 2.8, or excuse me, 2.18 standard deviations. You could say away from the mean, and that's totally fine. If you want to be more descriptive, you could say above the mean, since that's a positive quantity. I'll go with that route and say 2.18 standard deviations above the mean. Again, I wouldn't say that's a required part to get full credit on a question like that, but it doesn't hurt because if you said it once above the mean, you'll know that the answer to this part was the lifetime. It better be larger than 885.33 because that is the mean. And we said it's above it. But now the question is, what is the lifetime of that light bulb? So now we need to actually solve. Well, sorry about that right there. I think that's kind of an unnecessary additional trick question on that one. But to solve this, well, let's see what we have. We have the z-score, that's supplied. We, of course, have the mean, standard deviation. We calculated those things. What's missing is the data value. So we'll just put in a variable. Y does the job. No harm if you did use X. I mean, that makes it more similar in algebra, solving for X. So we'll go first. I'll just state the formula. Z equals Y minus Y bar divided by S. Okay, well, we're pretty much done with the formula, so let's eliminate this next. Now we plug in the information that we know we have. So Z is 2.18 on the left. Just like before, calculating interquartile range or the z-score above, just a whole bunch of substitutions. We're just plugging in that quantity in for Z. On the right-hand side, we don't know the value of Y. That's our one unknown, so we'll just plug that in. Minus our Y bar. It's above on the notes, but following the color coding, it's also this right here, 885.33. And whole thing is divided by S, which is the 69.68. So our goal is to solve for Y. Standard thing you'd want to do is definitely just clear the denominator. We're going to be multiplying both sides by 69.68. But this is legitimate algebra, and algebra is not a major part of this class. It's not a major prerequisite either for this class. Let's do this one super carefully this time. We did it on the end of class, I believe, on Thursday when we were solving for one. But this time, if we're indicating steps, here's what I would personally do each and every time. Step one, multiply 2.18 by 69.68. So let's do that right away in the calculator. So whatever is on the left-hand side, we're multiplying by the denominator, essentially by that first step. This is a very common equation when we don't solve a lot of equations. So this is a step-by-step guide. If you don't like these kinds of things, works really well for the notes. You're not going to get too many different kinds of weird equations on the exam. It'll be something like this. So let's go taking 2.18 times 69.68. And here's our result. We're rounding our result to one decimal place, but I'll just keep all the precision we've got just to have more accuracy. So take this number, it goes on the left, 151.9024 equals Y minus 885.33. Really, this is step two, so let's say it right here. Step two, write the result of multiplication here. So effectively, if you like cross products, it was just a halfway cross product. It multiplied across in that kind of way. Any questions to that step? Okay, continuing forward. Last thing to do to solve for y, what would you all do at this stage? Exactly. Really, this is the uncomfortable equation, right? Dealing with fractions just feels like there's higher level of complexity. But here, it's a little bit more routine. Let's write in as a step regardless. Step 3. Notice there is always a negative sign in the z-score formula, no matter what. So the only thing you could possibly change this up is if you had a double negative. But in this format, with a negative there, add 885.33 to the left side. And let's say that's our last step because we're essentially done. In the calculator, this is what it looks like. We already have the left-hand side put in, just go plus 885.33. And that's going to be our result. So we have, depending on how you like to write your result, usually for me, if y is on the right, I leave it on the right. That just looks funny. Some people prefer just writing it this way. I'll go this route. Totally up to you which side y is on. Let's write y equals 1037 point. This is a good time to round to one decimal place. It'd be 0.2 hours. Well, we said it was 2.18 standard deviations above the mean. The mean is 885.33 hours. It's like we're adding 72.5 times, or no, excuse me, 2.18 times. So that seems like it's in the true right neighborhood. Any questions, folks, with that result? Okay, so this was an exceptional light bulb. Notice all the data looks like between about 968 down to 769 hours. So the moment you're starting to say 2 standard deviations or more, that's actually quite a lot. It's exceptional. It's 1,000 hours, over 1,000 hours, bigger than anything in the data set. If we said 3 standard deviations or more, it's more than exceptional. It's like almost a guaranteed outlier. Those are becoming very unique observations at that point. So that gives us a feel of what is a standard deviation. Things within 1 standard deviation are typical. Going beyond 2 standard deviations, you're getting more and more atypical observations. I think we did it, folks. That's the end of part C and the example. Any questions at all getting through this one? Okay, so think of example 1, example 2. We're working with z-scores, but we didn't do anything too amazing with them, admittedly. We're mostly just practicing with the formula, finding a z-score or solving for a data value, like in this problem. But here's a case where the z-scores are actually pretty useful. Looks like we did some preliminary highlighting on this. So let's start over and take a look at what's going on. It says a student took 2 national aptitude tests. Mean and standard deviation were 475, 100, respectively for the first test, 30 and 8, respectively for the second test. That's just 2 sentences in, but that's a fantastic amount of information to organize. They tell us next, students scored 625 points on the first test, 45 points on the second test. You can imagine this is like a SAT exam versus a ACT exam. Seems like it's about right. So the question now is, which test did the student do the best on? And it's really hard to tell just based off this information. I have no clue really. But that's where the z-scores start to become pretty helpful. Z-scores will tell you which exam was really done best by measuring how many standard deviations 625 is away from the mean, and how many standard deviations 45 is away from the mean. Notice looking at this number alone is not good enough. We have to think in terms of standard deviations. It's not just about the center, it's also about the spread or variability. So if you see a question like this one, I think there's one in the homework in MyStats lab, could be a potential exam question. Really the major strategy here is just to organize. When it said 2 national aptitude tests, let's say there's test 1, just generically, test 1, whatever it is, test 2. So we're splitting up our information this way, because I like a table, so let's go that way. Up to you how you like to organize. Then a bunch of statistics were given. Well, let's read this really carefully. The word respectively is kind of confusing, but it's used a lot to just write a sentence really fast without saying the same things multiple times over. Respectively causes a correspondence. If they said mean first, then because they said respectively, after they gave two numbers, the mean is the first number. So that's all respectively means. There's a correspondence with the first element to the first number, and there's another correspondence with the second element and the second number. Does that make sense to folks on how that sentence is written? It's admittedly not the nicest way to write a question, especially if it was an exam setting, but this is so common that I left the question written in this way just so that we face it. It's something you can see on legitimate homework problems in the book. Okay, so they said that was for the first test. Now we move over. 30 and 8 respectively for the second test. Respectively came up again, so we mean the mean was 30. Standard deviation was 8 on the second test. Here's where I'd start writing down symbols. So test 1 is relative to those numbers. Y bar for the mean is 475. S for the standard deviation is 100. Then we just do it all over again. This information is relative to the second test. So go over here. The mean is 30. Standard deviation S is 8. So we're taking a lot of time just to get down to here. But I assure you, this is always a great idea. You have really dense information. It's all about organizing at this point to really see what's going on. Now they tell us here, the student scored 625 on the first test, 45 on the second test. Those are specific data values. We're color coding them in yellow on these entire set of notes. So let's keep that pattern. So we'll say Y, just an ordinary data value, 625 on the first test. For the other data value, it's 45 on the second test. So far, all I've done is I've taken this and I just broke it down into tabular form. So we can actually see the information, not read through it a bunch of times trying to grab the elements out. The question of this is, well, that's more of a directive than a question. They're asking us to use z-scores to determine which exam the student performed better relative to the other test takers. Looking at this as it stands, anyone see which one it seems like the student did better on, or does it look like it's just too hard to tell? Sorry, say again? Test 1 potentially? Yeah, here's the thing that's kind of tricky about this. If you look at this problem and you eliminate the standard deviations, then, well, this starts to look pretty good, right? But this one is 15 points above. Maybe this one's a little bit better because that's like half of the mean. It's really hard to tell. I honestly don't know. We'd have to calculate to be sure. It kind of is a pot shot to me, unless there's something really spectacular going on with the standard deviations. And there kind of is. This one's huge. That one is small. So whenever you're looking at this kind of information, the mean alone is never the full story. The standard deviation is just as important. So that's kind of the big takeaway for these kinds of things. And honestly, I still don't know, so let's calculate it for sure. Z-score formula goes Z equals data value Y minus its mean, Y bar, divided by its standard deviation, S. This is where the organization is super helpful because looking at the Z-score, there are 3 formulas on the right-hand side, but if there's 2 exams, there's really 6 different variables rather on the right-hand side we have to account for. So the organization tells us, well, over here, we're just putting in 625 minus 475, division by 100. So let's go to the calculator then. 1.5 things. So this would be 1.5 standard deviations. And that's pretty amazing. If you're more than one standard deviation away from stuff, that's remarkable. It's not like 4 or 5 standard deviations, but that still says this was exemplary work on test 1 for sure. If this comes out, let's imagine if it was 1.4 standard deviations, what test would you say the student did better on? Exactly. So the higher the z-score is, the better the student would have done in this context. I don't think it's 1.4. Let's calculate it and see what it is exactly. So z equals
47, 30, 415. I got one.
45 minus 30 over 8. We have a debate on the answer. That's always a good thing. Let's check it out on the calculator to see how it goes. I did it once with parentheses on the numerator, but here's another style that's just as fast. Some people like better. Just do the numerator, 45 minus 30. Hit enter. Hit divide by 8. And 1.875. Standard deviations. Absolutely. The student looks like did much better on test 2. And it doesn't seem like by much, but that's 0.375 standard deviations, almost a half a standard deviation, in other words. That is substantial. I would say the student did substantially better on test 2. Maybe what happened was the student took test 1 first, saw a lot of information, thought about it, went and took test 2 afterwards, maybe studying more, and just naturally did better, even though it was a different exam. But we'll say here, to finalize the problem, the student did better on test 2 since that z-score is higher. Well, we did it, folks. That's our discussion on z-scores. Any questions or comments about any of this so far? Okay. So z-scores, they're kind of a nice trick. This is my best attempt, and same with the book. Best attempt of an example where z-scores are actually pretty important. It's, as the author says, like comparing apples to oranges when you have totally different exams with different ways of scoring them. Lots of algebra, yeah. But another thing that comes back, let's just put this as a preview on the notes. We'll look at z-scores a lot in so-called hypothesis testing. We're going to turn back to these notes just to remind ourselves what we did. So this is going to be a few chapters away. I forget the exact chapter. It's been a while since I read through this book. But in hypothesis testing, z-scores turn into test statistics. So our author is introducing it now. It's important to talk about before we go to the normal distribution. But this is where we're majorly going to be really thinking about z-scores a lot more. Down the line, when we're probably getting close to Thanksgiving break, is when this is going to come up again. Well, that's the conclusion of these notes here. In the homework, you're going to be doing a lot of the similar kinds of things, calculating z-scores, solving for a data value. And there's a couple problems of doing essentially this kind of thing, comparing apples to oranges again. Any questions or comments, folks, before we go to the next section then? Okay, let's save this up. And now off to the next section. And by the way, we mentioned this before, but it's always good to kind of reiterate some stuff. We're in week 5, and the things we said in week 1 could be getting foggy by now. I know they are for me. These get re-uploaded again with the full solutions once I get a chance after class. So you can always come back here to see the full solutions. If you ever need a blank copy of any of these notes, they are all always uploaded here. By the way, I do get forgetful, so if I just missed putting something in, let me know and I'll get it put in. Also kind of annoying that chapter and the sections kind of don't organize well. So find your chapters on the bottom, and then the sections are in the numerical order you would expect. So those are where the blank notes are. And if you miss a class, it's okay. You can always come back to see what we did by going to the recorded lectures right here. So that's our full playlist on YouTube. And again, things can go wrong here. I have to add the video to the right playlist. So if for any reason I just forgot or put it in the wrong class, it'll be missing here. Don't ever hesitate to email me and say, hey, Mike, what happened to the video on Wednesday? Something like that, and I'll look into it and fix it right away. So back to where we're at. We're now in section 5.2, shifting and scaling. This one is kind of an odd section. I really didn't know what to do with it in the notes, but it is important. It's kind of a review section in a certain sense. So let's take a look at it. And it starts with a bunch of organizing information. Let me first get the windows in the right spot. That should do the job. So here's our section on shifting and scaling. It is a review section in a certain sense. We'll cover more information with it. But it's a good way to take a full inventory of every statistic we've seen so far. So what do we mean by shifting the data? It means you take a data set, like the light bulbs with the 6 observations, and you add or subtract the same number to every single observation. Why would you do that? Well, maybe they found out their experiment was wrong. The light bulbs actually ran for 100 hours, but it wasn't recorded. They'd have to add 100 hours to all of the observations. If we are rescaling the data means you're multiplying observations or dividing observations by some constant. Why would we do that? Well, if you're thinking about the light bulbs in hours, maybe we want to write them in minutes. Maybe that's just more relevant. We would have to multiply everything by 60 minutes to the 1 hour. So this is a theorem, which just is a way to say it's a mathematical fact about the objects we're working on. It says here, if we shift the data by adding the same constant or subtracting the same constant to every data value, it'll leave the measures of position, or excuse me, we have to add or subtract the same value to measures of position, but measures of spread are left unchanged. That's a really confusing statement. So this is our first look at the theorem. We're going to look at it again in context with actual data so we can understand it better. So I thought, first, we're just looking at the actual theorems. It's confusing and vague at first, because it's not even saying what are the measures of position, what are the measures of spread. That's what we'll do in example 1. Rescaling the data is different though. If you rescale the data by multiplying everything or dividing everything by the same constant, it affects all measures of position and affects all measures of spread. Up here, shifting does not affect measures of spread. That's really kind of weird again. But before we get a really good discussion going on that, we need to talk about measures of position. Example 1 says, complete the following table by indicating all measures of position, all measures of spread introduced in this course. Really vague how it's written, but I'll go first. One measure of position is the center. 2 ways to measure the center. One is Y bar, sample mean. Anyone know a different way to measure the center? Absolutely. If our data is skewed enough, we use the median M, sample median. So those are the common ones we often think about if we're thinking center. Center is one position. There are other positions. Anyone know a different measure of position we could throw on here? Not quite range or RQR. Those are more spread. That tells out how spread out the data are. Exactly. Let's put that in now that you mentioned it. Measures of spread are how spread out the data are. The most blunt one is range, which is the minimum minus the maximum. So it's pretty blunt, but it gives you information. Better information is interquartile range. We're looking at the central 50%. Sorry, say again. Oh, dang it. Yeah, that would give us a negative number. It is backwards. Thanks for spotting that. Getting a negative number is worrying on your range. If you take the negative sign on, you're right, but that's better done by just putting the formula in, right? Thanks for spotting that. Maximum minus minimum, only because we want a positive number for our range. The other one you mentioned is IQR, interquartile range, and let me not make the similar mistake. That's quartile 3, the upper one, minus quartile 1, the lower one. But wait, there's more. There's more on the measures of position. There's more on measures of spread. Anyone spot what's missing?
Standard deviation.
Yeah. It's not a measure of position, it would be a measure of spread. So standard deviation is how spread out your data is. So it would go here. S, sample, standard, deviation. And just to clarify a little bit more about S, how is it a measure of spread? You could think of it in these terms. Or at least roughly symmetric data approximately 68% of all observations are between y bar minus s. So you go one standard deviation to the left of the mean. And I don't know why I put a comma there. Let me take that off. That's just confusing. And y bar plus s. Similar to the interquartile range. The interquartile range captures the central 50%. Standard deviation is capturing the central 68% if you subtract s from the mean and then add s to the mean, the standard deviation. We'll return to that. This is getting closer to the normal distribution. And some folks might think of this in terms of the 68, 95, 99.7 rule or the empirical rule. So that's coming up in the next sections. So all these tell us how spread out our data is. And we did it, folks. Those are all of the measures of spread we've introduced in the course. Range is one where it's more of a trick question. If you didn't put that in there, I'd still say you got this question in spirit. If you left that off, you'll notice we've only calculated range like maybe once or twice. But stuff is missing here. Anyone see what measures of position are missing? Yeah, absolutely. Min and max are absolutely measures of position. And there's two more. Here's a hint though. Why is the median, or excuse me, why is the sample median a measure of position? Not quite lowercase sigma, because what sigma is, exactly, yeah. Lowercase sigma is the population. Standard deviation. But yeah, absolutely. The median is the 50th percentile, but there's other percentiles just as good. So they refer to position. They are quartile 1. We could call it quartile 1, but if we're thinking of measures of position, it's probably better just to say, sorry, go ahead.
Oh, 25%. Right?
Yeah, exactly. Better just say 25 percentile, because that's how it reminds us it's position. So it's the 25th percentile. And last is quartile 3, which is the 75th percentile. Looking at this table, you might have said, well, I could have done this a little bit better, and I agree with you. This was kind of more of a class activity, just coming up with the statistics. But another way to think about measures of position is it's the 5-number summary, and y bar is pretty much what we produced. 5-number summary is the minimum, quartile 1, median, quartile 3, and then the maximum. And we just throw in y bar as well. So there it all is, the measures of position, measures of spread. And looking at the theorem again, it's saying if you add or subtract the same value to every single data value in your data set, every single one of these are going to change, but not your measures of spread. Why is that? Well, you're just taking your data and shifting it. Every observation, it's still spread out by the same amount. But that's just me waving my hands. The best way to see it is to really see it happen with real data. So that's what we're going to do next on example 2. Any questions first, folks, with the discussion on this one?
If the maximum and minimum change, how does the range not change?
The range would change along, well, let me see here. I see what you're saying. Let's say for just a quick example, let's say the minimum was 3, maximum is 5. So then the range on this one is going to be 2, right? But now let's say we're going to add some numbers to every single data observation. That would change these, right? That would mean, let's say what we're doing is just add 2 to make it simple. Add 2 to every single observation. Minimum here is now 5. Maximum here is now 7. Oh, I did it backwards. I did the minimum minus the max. I'm not sure. I feel like I'm going in order, smallest to largest. Maybe that's what's going on in my head. But somehow, some way, it's still just a 2. But the critical thing is we had to have added 2 to every single data value in the data set. Other questions about that so far?
It's the same value that you add.
Exactly.
So we're gonna do where we just put this in that, not necessarily, but that is. Okay.
Exactly. So shifting the data just meant you shifted everything, max, min, every single observation, but the distance between max and min is left unchanged. Turns out it's the same with the interquartile range. It's the same with the standard deviation. I think that's more surprising. It's harder to see. That's what makes it a theorem. You have to do math to really prove it's true.
If we had written standard deviation, what's the difference between that and sample standard deviation?
It would be the same. Here I'm just emphasizing it's different from lowercase sigma, the population standard deviation. But all the emphasis on sample mean, sample median, sample standard deviation, you could take out the sample and we would still be saying the same thing with that symbol. Other questions at the moment? Okay, let's take a look then at the same theorem, but just a different view. So here we're just looking at the statistics, talking about the theorem, but here's some actual real data. I mean, this is real data. I was going to say real made up data. I think this is from a legitimate study. There's a random sample of 15 needles taken from different parts of several, I'm not sure how to pronounce that. I'll just say Aleppo pine trees located in Southern California. So we have a sample size of 15 needles, and it's 15. And let's see. Looking at this, I feel like there's something missing in this description. Probably a better write-up of the problem should have said, let's add it here. The observations are lengths measured in centimeters. Sorry for that omission. That's kind of a foggy question unless you say what these numbers really are. That is a revision right after the fact. So I'll put it in red to say we need to add that in to make the problem clearer. So 15 pine needles, they measured each one of them in centimeters. This one was a really large one. There's some smaller ones in here. And that's the histogram of all the pine needles put into one distribution. We also have a sample mean of 9.59 centimeters, sample standard deviation of 1.59 centimeters. But this one is a measure of position. It's measuring the center. This is a measure of spread. So what are we going to do? We're going to shift the data as this part of the theorem, same thing as above, just put into the problem. We're going to subtract 5 centimeters from every single observation. Observe that if you did that, you're literally just taking this whole histogram and moving it over to the left. When you replot it, it doesn't seem like that happened unless you look at the horizontal axis. Subtracting 5 means the minimum went down to 2. If 7 was a real minimum, it was really a 7.2. Going down to 6.2 or 5.2. Sorry, that was a little hard for me to subtract. So every single one of these values just got subtracted by 5. Then I just went into a calculator. I didn't actually subtract all 5 on the notes, but you could if you really wanted to import it into the calculator to double check. I felt that'd be way too tedious for class. So I just went into the calculator, calculated the sample mean, sample standard deviation for these data. Here's the results. And notice what's happened. Measure of position does in fact change. It went down by 5. So this moved down by 5, but the standard deviation, that's a measure of how spread out the data is. And it's still spread out to the same degree. It just got moved over and it's still exactly 1.59 centimeters. So that's kind of a remarkable fact in a certain sense. But would you feel it's believable that that's really the case? Standard deviation doesn't change. Also, glad to hear that from folks. You can definitely test it. So if you're the skeptical sort, I respect that. You can go in your calculator and go like this. Hit stat, enter. Up arrow, clear this out. This is just a demonstration. We won't do the whole thing, but go 7.2 minus 5, import all of your data like that. Go run the statistics, and this is what you'll produce. You'll notice the sample mean changed, but not the standard deviation.
Did you write that -5 in the actual
Up here?
calculator like that?
Yeah, absolutely. You could do a whole bunch of computations right inside here. So if you have 7.6, if you're rescaling, go -5, and it'll do all those computations right inside here. Kind of cool in a way. You could do weird stuff in this calculator. But other questions about that so far? Okay, so that's what's going on with shifting the data. The punchline to shifting the data is it left measures of spread unchanged. So let's highlight that just to emphasize. That is unchanged. So rescaling data does only one thing, moves all of your measures of position, which means it affects every single thing in this table right here. This becomes almost like a cheat sheet when you're doing the homework problems in this section, because if any one of these statistics comes up, you'll know they're talking about measures of position, and that's how the theorem affects it. But now, rescaling the data is different. Rescaling the data means you're multiplying or dividing all observations by the same quantity. And what I did was, on this problem, I multiplied all 15 observations by 10. And let's double check just to see if that's believable. Here's the original distribution. Here's the distribution after rescaling. So notice 7 went up to 70, 13 went up to 130. So it looks like we truly did multiply everything by 10. Yeah, exactly. Same shape, just different position on the axis. I probably shouldn't say it that way. Different numbers on the axis down below.
Would you say that was still to the right?
I would say definitely a right skew on this one. Potentially bimodal, a little bit debatable with that block right here. But let's take a look at the statistics. Originally, they were these values. Just a quick screenshot here. But once we multiplied all data values by 10, they became these values up here. It's now 95.9 centimeters. That was multiplied by 10. And standard deviation was 1.59 multiplied by 10, and it goes to 15.9. So that's what's being said with rescaling the data. It's going to multiply or divide all measures of position. So that's why this changed by 10, as well as, this deserves emphasis, serious emphasis. Let's bump that up. As well as all measures of spread. Maybe that's a little too much. There we go. So this is the one time you do affect the standard deviation S right here, if you're multiplying or dividing all data values by the same quantity. So if that happens, well, things are more spread out now. It's going from 70 to 130 versus a spread of 7 to 13. This has a range of 5, but this has a range of 50. So standard deviation should be reflected there. And in fact, it does. It goes up by just times 10. Well, that's a pretty technical theorem, and this is just my attempt to show how it works with actual data. Any questions or comments at all, folks, with these descriptions here? Okay, takes a while to actually say all this kind of stuff and explain why it's plausible, how it goes, what it looks like with real data. But this is not how the actual problems look like in this section. The problems in this section look a little bit more like this. This is a shorter section, and my two examples here are a little bit longer than what's actually in my stats lab. But this is essentially what we're doing in this section. Example 2 says, a study of 130 healthy men, so they gave us a sample size, 130, and women found that the mean temperature was 98.25 degrees. They gave us a statistic in Fahrenheit. Oh, hang on, let me fix that. So next thing I'd probably want to write down here is, without switching the color coding, so put that to blue. We have a sample mean. Y bar is 98.25 degrees Fahrenheit. So that's our mean temperature in that group. Sounds about right. 98.6 degrees is often quoted. It's not fully accurate. That's pretty old data. So that seems reliable. And the standard deviation was 0.73 degrees Fahrenheit. So here, S, that's what they're referring to, will be equal to 0.73 degrees Fahrenheit. So the way I wrote these out are, Y bar is actually the sample mean. They didn't say that directly, but it's implied because they said they took the 130 healthy men and women, found the mean. They're saying the mean of the sample. So that's why we're using Y bar and S to describe those two values. They're true statistics. They gave us more. The min temperature is 96.3 degrees. Let's put that in. Max was 100. This person probably had a fever, 108 degrees Fahrenheit. Probably should have been excused from the experiment, but they kept the data. Maybe that's the person's normal body temperature. There's a lot of variation in just humans as well in their bodies. So that's kind of amazing maximum temperature. Oh, I see. So it could have been something like that going on. Who knows? It could have been something like rheumatoid arthritis could give you some weird different body temperatures, lots of different conditions. So now they say, well, this is all in Fahrenheit. Imagine you're a doctor that works in, say, Europe, using the metric system. You're not using Fahrenheit, you're using Celsius more likely, or something else. They say find the mean standard deviation, min and max of the temperatures, but in Celsius. Good news is they gave us a formula at least. Here's the formula to convert. The bad news is we have to break this down. Think in terms of shifting and scaling. So let's take a look at that formula again. C equals 5/9. We're going to use the distributive law and multiply it here because it's a good idea to break down this formula a little bit more. 5/9 times F minus 5/9 times 32. We can plug that into the calculator. So if you like a fraction, here's a little trick in your calculator. You can go first 5 divided by 9 times 32. So here's your decimal number. That's totally fine to put in 17.7 bar, 17.777. Happy with those numbers. But if you want a fraction, you have some powerful technology. You go to the math key. Of course, it's got to be there, right? Oh, sorry. Yeah, I've got to put in a negative on that. So let's go. Might as well just put it in again. Minus 5 divided by 9 times 32. Thanks for spotting that. We need the negative when we go to put this in right here. I have to remember I already have the negative written in. So I'll just put in the number afterwards. But now that you have that number, again, I'm okay with the decimal number, but for a fraction, here's the steps. Hit the math key right here. And notice option 1 says arrow frac. Arrows convert to fraction. So it automatically defaults to, that's the first thing the calculator thinks you probably want to use if you hit the math key. Hit that right away. Answer refers to the prior answer above, is being converted to a fraction. Now it gets negative 1/69. Again, it's totally optional. I think I would prefer the fraction myself, so I'd write that in. You're okay with the decimal number if you prefer that instead. So I'll go with negative 160 ninths. So there's our function, or there's our formula again, after using the distributive law. But there's a really important reason why we did this. If you look at this part, is that shifting or scaling? I heard a shh. I agree with you. That's shift by subtract 169ths from all the 130 data values, which means you'd be subtracting it from all these values when you get to that part of the formula. So this is shifting. Shifting means adding or subtracting the same number to everything. What about this? That's multiplying, right? So that would be rescaling. Rescaling is multiplying everything or dividing everything by the same quantity. So we'll call this scaling. So now that we've done that, looking at our statistics on the right here that we labeled, we have a theorem that says scaling affects everything, but shifting only affects measures of position, not the measures of the spread. So along this list, which ones would you say is a measure of spread? Absolutely, good call. So this one is measure of spread. All right here. The rest are all measures of position. So let's recall what the theorem above said when we were looking at those data values. The measure of spread is unaffected by shifting, totally unaffected. So when we go to convert the standard deviation, we only use that part of the formula. We ignore this shifting part entirely. That's some weird math, but it's because it's using those weird theorems right above. However, for everything else, these two here and the one above, you use the entire formula because those are all measures of position. Measures of position are affected by both scaling and shifting all at the same time. So again, that's a lot to think about. Any questions or comments at the moment?
So, I'm sorry, kind of to go back, when you talked about you prefer using fractions, if we wanted to use decimals, to rewrite that equation, we would just do C is equal to whatever 5/9 is times F minus.
Yeah. So it'd be,
Oh,
yeah, so we'd put the 0.5 bar here essentially. Then, oh, forgot the negative sign again, minus 160 ninths. And that would go in this location here.
yeah, where did
The 32,
it go?
that came from when I multiplied here to here. Oh, let me get that arrow going. When I multiplied here to here, that's what gave us the 5/9 F.
Right.
And then I multiplied here to here. So I went, let me clear that out just to show it again. Oh, no, you're fine. No worries. 5 divided by 9 times that negative 32
Okay.
gave me that quantity there.
And then you turn that into back.
Yeah, absolutely. I went here, math, fraction, converted over, and it gave me that. Totally optional though. So just to emphasize, you could also write this as C equals 5 divided by 9. Let's put that in. So 0.5 bar F minus 1/69 we have here, 17.7 bar. I think this is more natural because, I mean, we're used to just cranking these out in the calculator. You get this number first.
How do you put a 0.7 bar in the calculator?
You can't. That's the downside of it. You have to literally go 777 a bunch of times to try to approximate it.
You have to punch in 777.
Exactly. You'd be rounding to 4 decimal places if you went that route. So if you want a 17.7 bar, you'd have to go 17 point something like that and give you good accuracy. Or you could just put in as much as you like. These are all just approximations every time you do that. That's the only reason I personally like the fraction. It's easy to type in and get the exact number. You just go 160 ninths and then you're all set. A little bit faster to put in, but honestly, that's just an opinion. I'd say go with whatever feels just the most natural. Let's put here just a strong 4 just to convey both formulas are totally fine. Other questions so far? This one right here?
5/9 he multiplied negative 32 by 5.
Yeah, and the calculator would like this.
Then the parentheses.
Oh, sorry, didn't mean to scribble on it. Let me get an actual highlighter here. So first, I went here to here, and that's what gave us that part right there, the 5/9 F. But then in the distributive law, you also have to multiply it out here against that negative 32. So in the calculator, it would have been 5 divide 9. Then I'm going to multiply by negative 32.
And the reason we need that equation, right, the one that you're making right now, is because we need to be able to input our minimum and maximum as F, right? Is that way we can't leave it as 5/9 over F minus 32?
Sorry, say again? I got a little lost on the question.
So
What? Yeah.
the reason we're making the new equation is because we can't use that F in the
Oh,
original.
You have to get rid of the brackets, you have to get rid of the parentheses.
well, the major reason that I broke it up was
The weakest species scale.
exactly, it's all mixed up in the original formula. And the measure spread here is only affected by scaling. So we need to expand the formula out, show where the scaling happens, where the shifting happens, so we know which statistics are affected. Really kind of a tricky problem. I appreciate the question so far. But did I answer fully the question about the 1/69ths that you were asking about? Gotcha, that's where we're at so far. Yeah. Any other questions with just expanding out the formula? Okay, so this is kind of rough. We're almost out of time, but I think we could do one just to tie it up. Then when we come back on Thursday's class, we'll refresh what we were saying here and go forward. So just for, let's say, the measure of spread, let's convert that one. We'll do it again once we come back on the Thursday's class. So S was 0.73 degrees Fahrenheit. But we want that in Celsius, so that's where the drama starts. You might think you have to use that formula, but it's not true. It actually gives you the wrong value. And the reason is the formula involves a scaling and a shifting. Let's scroll up for just a moment. The theorem said that if you rescale the data, all measures of position as well as measures of spread are changed. You have to use the full formula. But when you shift the data, it leaves measures of spread unchanged. So the shifting part is that right there, the minus 1/69ths.
When we scale, everything changes.
Everything, yeah. Positions, exactly. So this shifting right here does not affect S. And so this means, we'll write this more cleanly when we have more time, but just for a preview where this is going, S in Fahrenheit is going to be 5/9 multiplied by F. That was the Fahrenheit value, 0.73 degrees. So that means we're taking 5 divided by 9 times 0.73, and our Celsius standard deviation is now 0.4, let's call it 0.41 degrees Celsius. We don't use that part of the formula because that's shifting everything to the left. However, measures of spread do never get actually shifted. So the whole purpose of breaking this down was to observe the shifting, or excuse me, the scaling and the shifting to see what part of the formula we're really going to use. But that's highly confusing. So we're going to refresh that. And we have a second problem as well so that we could get more additional practice on it.
Okay.
Does that help so far in the direction we're going at the moment?
Yeah, we needed to break up this problem because when we scale, everything changes, but because our problem only involves shifting, we have to change the equation so no measures of spread are affected.
Exactly what we're doing, yeah.
Got it.
Lots of stuff to jump through on this kind of problem. Any other last questions, folks, before we call it a night? Okay, have a great night, everyone. Stay dry, drive safe, and we'll be right back in here next class. We'll also be moving over to section 5.3 as well to see how this kind of stuff ties together.
When you started doing the second equation, you're like, why do we need the second
Yeah.
equation?
I mean, the formula looks just fine as it is, but then all of a sudden things go wrong. It's really kind of weird, surprising even.
I don't like we have to figure out what problem we can actually try and solve.
Yeah, it's unnatural. In a math class, this never really happens. If you're given a formula, you just use it. But now in the statistics class, it's different.
Statistics, there's like never.
There's 3 right now, too.
Yeah,
Yeah.
yeah, exactly.
Yeah.
It is weird for sure.
did this yesterday, and yesterday, like, I know how to do this, why doesn't it make sense?
Yeah. I appreciate the questions though.
Yeah, sorry I had to step out, my kids, so I had to make sure they had right phone.
Oh, no worries. Yeah.
Stupid,